So here we're going to be going over a typical spring problem that you'll see in the work section of Calculus 2. So I want to do a few things to start out. First of all, notice that we are in metric. Our units are in metric. And so at the end, when we find the work, that's going to be represented in joules, which is Newton meters. So I'm going to go ahead and convert all of these centimeter values to meters at the very beginning. I think that is just easiest for me, just so that I don't forget. And so this is going to be 0.1 meters. What else do we got? This will be 0.2 meters. And then this will be 0.14 meters and 0.19 meters. And then we don't have to worry about that later on. And now let's actually jump into the problem. So our usual goal here is going to be to solve for our spring constant. And so first, I like to write down my known, I guess, formulas, we can call them, for our spring problems. So we know that the variable force, f of x, is equal to our spring constant, k, times x, where x is the number of units beyond our natural length. Maybe we should write that down. So k here is my spring constant. Which is what I'm going to be trying to solve for, because obviously it's not given in the statement of the problem. And then we are x units beyond the natural length of the spring. Okay. And then the other thing we know is that work is equal to the integral from sum a to b of our variable force. But luckily enough, we know how to represent our variable force for the spring problems. It is that k times x. We can go ahead and write work as the integral of kx dx. And so the reason I write these two down is to decide which one I'm going to use to solve for k. So the problem is usually set up so at the beginning, the first sentence or two gives you the information you need to solve for k. And then at the very end, you have a question to answer. So this question that I'm answering about how much work, I'm going to save for the end. I'm going to ignore everything in the red brackets for now and focus on everything else. So I have a spring that has a natural length of 0.1 meter. And it tells me that it's going to take a 22 Newton force to keep it stretched to 0.2 meters. And so what does it give me? Does it give me force or does it give me work? And it does give me the force necessary to stretch the spring. And so I must be using this first formula to solve for k. And so I'm going to come over here and say my variable force is equal to k times x. And so I know I want to be solving for k, so I must be able to fill in my force as well as how far beyond my natural length I am. So the force that I need is 22 newtons. I'll leave k blank. And then how far past my natural length am I? Well, I'm ending up at 0.2 meters, and I started at my natural length of 0.1 meters. And so I get 22 equal to 0.1 k. Then I'll divide by 0.1, and that'll give me 220. And so there is my spring constant k. Okay, so that was my first goal, was to determine k. Now I can look at the question inside the red brackets that I was trying to answer. Now I want to know how much work is required to stretch from 0.14 to 0.19 meters. So first, let's just set ourselves up. So we know that work is equal to the integral from a to b of kx dx. First, let's leave our limits of integration blank just for a second. I'm going to fill in k. Now I'm going to figure out what A and B are going to be. So if it's not clear, or if you haven't seen this yet, this is going to be B units past the natural length. Similarly, you're looking for A units past or beyond, I guess is the better word, the natural length. Either way, as long as you understand what I'm getting at. And so you need to be very careful. A lot of students are tempted to integrate from 0.14 to 0.19, but that would be incorrect. I want to know how far past the natural length these values are. So I'm going to start at 0.14 and then subtract my natural length, which is 0.1. Then I want to end up at 0.19 and subtract my natural length. Okay. And now from here, it's all just about integrating. So let me fix this and then we'll continue. So this will be 0.04 and this will be 0.09 and then we have 220 x dx. Now I'll pull my constant and integrate x. So we'll get x squared over 2 from 0.04 to 0.09. And I'll go ahead and divide my 2, so that'll give me 110 here on the outside. And then I have 0.09 squared minus 0.04 squared. So here I have 110, and inside my brackets or parentheses, I have 0.0081 minus 0.0016. So we have 110 multiplied by 0.0065. And then I imagine you'll need a calculator here, and we get 0.715. And you notice that I was very, very lazy about my units. I tend to just not write them down until the end, which is probably bad, but that's just the way I do it. And my work here should be in joules.